In Chapter 9, we look at frequency analysis. When we measure our data, our variables can either be numeric or character. Character variables are then typically defined groups. Numeric variables can be ordinal or nominal as well, and also define groups. So these variables that define groups have a number of what we call classes represented, and that's usually some kind of a small finite value. We could look at testing the distribution of these number of classes for each of the variables to see if they fit a particular distribution, or we can look at two at a time and see if they're somehow related to each other. All of these are types of scenarios that can be tested using a Pearson chi-square test. So the categorical and data analyses courses include these introductory methods. There are more advanced methods also, and there are more advanced methods that handle more than two variables. They're beyond the scope of this book, but that's what you would need to look at is a categorical reference. In Chapter 2 in this course, we introduced a test data set where we just looked at the letter grades on the tests, and we only had a very small class. There were only 6 students here. So this is if I looked at a frequency bar chart of the grades here, and so that in practical use for purposes of this chi-square test, we have a much larger class. Perhaps we have several classes and we're looking at the overall distribution of the grades. We might ask then, do these grades occur with equal frequency? Then also, what didn't happen for us is there were no D's or F's, and as an instructor I hope that never happens as well. But we would, if we look at a larger group, a larger sample, that certainly may be possible. So we may be asking, do these occur with equal frequency? Or say, are at least 25% of the grades A's, B's a given percent, C is a given percent, and such that those percentages all add up to 100. We can test those using a one-way analysis. Okay, so there are 2 different ways to do that. First, the test, do they all occur with the same proportion? P1 equals P2 up through P sub K, where K is the number of classes we've determined. Well, how the test statistic is calculated is that how many did you observe in that classification minus how many did you expect under this null hypothesis, and that those differences can be either positive or negative, so we square them so everything's positive, divide by the number of expected, and that's what is our chi-square test statistic. This particular chi-square test statistic has K minus 1 degrees of freedom, and we'd reject the null hypothesis of equal proportion for chi-square test statistics that are large. Likewise, we can look at a goodness of fit test for a nominal distribution. Typically, when we say goodness of fit test, this is kind of what people are thinking about, is that they have those K different classes and they look at the hypothesized values. So here P1 equals P1 star, where P1 star is a value between 0 and 1 is a proportion, and PK star is some value between 0 and 1. The constraint is that these PI stars are all between 0 and 1, and that they sum up to 1. That is, it is a discrete probability density. Once again, you compute the test statistic the same way. How many did you observe in that classification minus how many were expected under this probability distribution, and we reject for large values of chi-square. In a two-way table, we have a row variable and a column variable, so think about this perhaps as maybe 2 different survey questions, a demographic question and an opinion on a local political issue. And so that you may have here then R different demographic levels and C different responses to this political issue. These values inside the table here are the observed frequencies. So the subscripts refer to row 1, column 1, row 1, column 2, and that those are the amounts that we observe. Those Nij values go into the test statistic here. So it says, is this demographic independent of this political issue? We could say they are either independent or dependent, and dependent we could also say related synonymously. And so that we compute the test statistic by looking at the observed frequency minus what's expected if they were independent. Again, those could be positive or negative. They're squared so that the chi-square statistic is always positive, and so we would reject for large values of chi-square. Degrees of freedom on this type of test changes from k-1 to it's going to be the number of rows minus 1 times the number of columns minus 1, and there are many more expected cell frequencies to look at. And I just use the term cell there. That's what each one of these row column combinations is referred to as a cell. Now, for both these one-way and two-way analyses, there are other test statistics that can be done. A chi-square analysis is one that requires a large amount of data, and so that we look for the expectations to be at least 5 in each cell, either one-way or two-way, in order for this test to be reliable. So for smaller sample sizes, those things you would need to consult and a categorical data reference such as Agresti that I have listed, and the SAS help and documentation. ProcFreq does do those options also. Now we could write more syntax here, but the 3 lines I'm focusing on are ProcFreq, tables, and weight. Very often all you need are the first 2. We'll illustrate what's going on with the weight statement in our data set here in this chapter. And of course we can always have by and where statements. We're not including those up here anymore. You know they exist. You know that for a by statement there must be a preliminary or a previous compatible sort done, and the where statement, data step information 2 in chapter 4 gave us syntax for specifying conditions in a where statement. The Freq procedure has a few options I've listed here. Probably the most useful to you would be the n levels and the order equals data or order equals frequency. You can, whenever you see a vertical bar like this, it means pick one. And so data is the default, I believe, and if you wanted order equals frequency, it's going to put things in a descending order according to frequency. How you request your analysis is done in a table statement. And so for a table statement, they can be a one-way table or a two-way table. So if we had variables A, B, C, D, E, F, you could request tables for some of them, such as A, B, and F. If you wanted to almost all here, there is a way you can do that also that uses the double dash. When you use a double dash here, so you can specify each one of them individually. When you use a double dash here, there is a caution there, and I encourage you to read section 20.1, that chapter on miscellaneous topics, to make sure that you're using that correctly. We can specify two-way tables in a table statement, and any one of these syntaxes are can be used. You can see the A star B, and so it's generally thought of as row asterisk column, if so that you do have that control on it, so that you know if you have a large number of levels for one of your variables but not for the other, you may want to put it as the row variable so it goes down the page. The table statement has options, so after your table requests, you put a / just like in some of the other procedures we've seen where they have options listed. Some of them are then control your printed output for one-way tables only, some for two-way tables, some for both. You can request the chi-square test, is the CHISQ, that you can do for both one-way and two-way tables. And we'll talk about this test P option. There's a test F option that works quite similarly. For objective 9.1, we need a data set called RTW, and that stands for right to work. The right to work data is for 202 subjects, so more specifically, right to work laws differ across states in the U.S. Right to work implies that an employee does not have to join a labor union in a workplace that is unionized. A random sample of 202 residents is taken, and each resident is surveyed regarding his or her opinion on right to work issues. And the employment status of the resident is also recorded. These results of the survey appear in table 9.3 of your textbook. And so When we look at the data here, I've also got totals for the rows and columns, so just be cautious here. Employment classification, I have industry, business, and unemployed. And then opinion on right to work, they either favor, do not favor, or they're undecided. The totals here on the right, these are the totals for each row. And at the bottom is the total for each column, and of course then a grand total for the 202 observations here. Now I've oversimplified things here a bit, just categorizing their classification in these three levels, and they could be, we could have other businesses or educational fields included here. In Objective 9.1, we need to create the RTW dataset containing employee classification, opinion, and why, where y is the frequency given in the table 9.3. Label, using the label statement, the variables in the right to work dataset. Conduct a chi-square goodness of fit for each equal probability of each level of opinion on right to work. Use alpha equals 0.05. Investigate the order of the data, order equals data option on the proc-freq statement and the inclusion of the weight statement. So we can do all of those. We create our data set. We want to input classification, opinion, and why. The dollar signs indicating that we're using text here. The label statement from Chapter 8. Then we can spell out employee classification, their opinion on right to work, and why was the observed frequency. So that's our RTW data set, and with the labels we'll stay with it. Okay, the frequency procedure will count the number of occurrences of the levels of the class variable and the employee classification variable and opinion. So here I have just opinion given here, and then in the next one, opinion. Let's scroll up, catch everything. Right, the very first one we wrote just the proc-freq. We didn't use a weight statement, and notice it had each opinion occurred only 3 times. Well, that is correct. If we go back to the program here, each opinion, I have 3 favors, 3 do not favors. If you want it to be counted more than once, then you have to use a weight statement and use that preliminary count, which is in our case y, that we have that information. And so if I go back here, then when I use the weight statement, then I get the 80, 90, and 32, which matches the table in our textbook if you look at the row totals there. Okay, also the thing that was going on here, I used order equals frequency, and so up here they went alphabetically in Objective 9.1 with no weight statement. I put the order in there, so I have order equals data, which is the F, DNF. If I could have put in order equals frequency and gotten another arrangement of this as well. The chi-square test statistics that we spoke about earlier, this is testing whether these occur in equal proportion, and it is evident that they do not occur in equal proportion with this p-value less than 1/10,000th. And then you can look at the deviations, relative deviation, so where it's taking observed minus expected, and looking at that percentage. And so we have 2 of them that occur with at a frequency higher than expected, and unemployed lower than expected. And we didn't anticipate that the unemployed would be there in the same numbers that the other 2 employed categories were. So that makes sense as well. In Objective 9.2, test whether or not employee classification in this population is 45% industry, 50% business, and 5% unemployed. Again, use alpha equals 0.05 in this goodness of fit test. So the alpha that we're testing, we're just comparing the p-value to alpha afterwards. It's not affecting any confidence intervals we're computing here, because there are none to compute. So here's our Objective 9.2. The test P, test proportion 45, 55, or you can put them in as 0.45, 0.5, 0.05. Just be consistent across there so SAS interprets that correctly. So you may need to run this classification first so it knows what order they are in, and so that it assigns the right order or the right percentage to the level. So we look at the output here. This part doesn't look any different than what we had seen before. The test percentages are in here, so this is how we can test whether or not we have the 45% industry, 50% business, 5% unemployed. So if our order is incorrect, this is the chance where we can see it and go fix it. And again, here it's not even we're not close to that, and so that we would reject at alpha equals 0.05. It gives me a deviation plot here again, so the relative deviation on the unemployed, I'm off by quite a bit. There is a test F option where F is you can put in the frequency values. I think perhaps proportions when we're starting out here are the more meaningful thing to look at. In Objective 9.3, is there evidence to indicate that a person's opinion concerning right to work depends on his or her employment status? That is, can it be concluded that the two variables are dependent? Again, conduct the test at the 0.05 level. And so I've got doing this two ways. First with the list option, so you can see how that works. Following table 9.3 in the book, there were some explanations of what those options did that you need to become familiar with. And then we'll just, this one we're actually doing the chi-square test statistics. So here we'll compute those. Here we are. The list option. So now I have two variables listed here. The row variable first, the column variable second. And so you can see how they're taking the information for two variables and all of those possible frequencies. And so if I didn't have the weight statement, all these frequencies would be 1. When I look at a two-way table, so this is without the list option, the two-way table is the default. This little cell right here is the legend for what you read in the table cells. So the top line is the frequency, that's the observed frequency, the percent out of all the data that are in this square, the percent out of the row that's in this, and then lastly is a column percent. So 20 is 9.9% of 202. 20 is 33.33% of 60. 20 is 25% of 80. And so that's how all those work. Now, not all those may be helpful to you, and we can suppress the ones we do not need. The results of the chi-square table appear here. And so it's testing whether or not there is an association between the employee classification and their opinion. And so notice there are several pieces of information here, and the chi-square test that we've discussed is actually this first row. Excuse me. The other two you'll pick up in a categorical data analysis course, and then these others are measures of association. And so at the 0.05 level, we would conclude here that the opinions on the right to work issue are related to the employment classification. In Objective 9.4, the frequency plot is a graphic illustrating the observed frequencies for the cells in the two-way table. Produce a frequency plot by adding the plots equals freq plot to the table statement of the second freq procedure in Objective 9.3. So this is the one where we generated the chi-square test statistic, order equals data. I'm not expecting any changes except for the addition of a plot. And so after the two-way table, it gives me this table. Now because my label for employment classification is so lengthy, here it crops it that I can't tell what these are labeled on the side. Opinion on right to work, I'm doing okay down here. And so it would be by inspection up above. The frequencies 20, 24, and 16 are here. So this first row is Indeed industry, the second row, you can confirm the 40, 51, and 9 from the second row. So this is the business row, and then this would be the unemployed. Now, if I had not created the labels, or if I rerun and say come up with an alternate data set for right to work that has no labels, then I would have the IB and the unemployed in printed over here at the right. Nothing changed right here. In objective 9.5, we want to repeat the objective 9.4, changing the frequency plot to a dot plot. And are we still having similar issues with the variable length? So here it's a frequency plot, and in parentheses I say I want to modify it to a dot plot. So everything still should look the same. Again, note on each one of these the wait Y statement is included everywhere. Everything's the same except for this dot plot, and so now it tells me the industry, business, and unemployed. Notice where it's labeled at by default, and notice they are in a different order than we saw previously. And so up here we have opinion on right to work favor, and there's plenty of space for that lengthy label there as well. So we can see the frequencies that they're on an x-axis here. So everything is kind of flipped 90 degrees on this particular illustration. Repeat objective 9.3 for the second frequency procedure, suppressing all of the default cell contents except the observed frequency. Include the expected frequency in the chi-square for independence. Produce only two-way analyses and no graphics. Alright, so if I don't request any graphics, I'm not going to get them, and so the plots equals is on the table statement, not on the proc freq statement again. I have the two-way table. I want it to do the chi-square analysis and suppress everything, it said, but the observed count. So no row percentages, no column percentages, no overall percentages, but do put the expected value there. Now these options can be in any order on the table statement, so there's not a preference there. And so if we look at all of these and run them, okay, now I have then just the observed frequencies in there, which we've recognized those now. The legend over here says the second value is the expected value. So if they are independent, this is what I would have expected. Okay, the farther it is from what I expect, it's indicating that they're not independent. And so that's what this chi-square statistic down here is measuring. It stayed the same everywhere, and it should have. So you can control how this table looks. You can control whether you get graphics or not, and you look at the chi-square analysis and make sure that you don't see a warning. Now, why would you see a warning? If your expectations, whether you print them or not, if the expectations in the process of that calculation are too small, that is, any expected value is below 5, then you will get a warning in your output. In your text, this is discussed, and so whatever percentage of the cells have expectations or expected counts that are too small, it'll indicate what that percentage is. And so therefore your chi-square test may not be valid, and so that's whenever you want to look at one of these small sample tests that available or overviewed in the Agresti reference or a categorical data analysis course. Additionally, whenever you're programming and you have a number of requests, we did things here where we had multiple proc-freq procedures. You can use more than one table statement. They can be a one-way analysis, two-way analysis. They can have different options. You can stack all of those up. Just remember that this wait statement Y is going to be applicable to all of these, and so that's something you need to be aware of. And I would encourage using single line comments or something similar to label what each of these is doing, so that you understand where they come from. And so that would be, again, single line comments are in section 20.2 of the book. A quick note about why we use the weight statement. Because of this observed frequency. And so otherwise, the frequency procedure, when you say frequency for opinion, it's the second variable. It's going to count how many times it encounters each opinion. That's what the frequency procedure does, is it counts. So if it needs, in order to get the combination IF 20 times, you would have to have, and without a weight statement, you would have to have 20 lines of data that had employee classification I, opinion F. You'd have to have that 20 times in your raw data. You would have to have 40 times employment classification B and opinion F. And likewise going through all of these different combinations so that you would have 202 lines of data in order to be able to do any of these analyses without the weight statement. So now if you're getting ready to conduct any kind of survey research, likely you do not need the weight statement because each one of your surveys that you code the responses, each survey is going to be a row of data. And so there is no preliminary counting that's going to be done if you're the one conducting the survey. Where we see this weight is if you're looking at someone's report, such as this example given here, or in textbook examples, they'll give you, here's the two-way data. Well, that preliminary counting has been done. So in practice, that preliminary counting is not done, and then we would not use the weight statement. So proceed with caution there on whether or not you need the weight statement and what you should be including in your lines of data.